Bending stress. So here are our learning outcomes. Understand how bending moments cause deformations in beams and apply fundamental equations to determine bending strain. Bending deformation of a straight member. The definition is deformation is caused in a straight prismatic beam when subjected to a bending moment. So here are some of the considerations. The beam must be prismatic and made of homogeneous material. The cross-section should be symmetrical about a single axis, and the bending moment is applied about an axis, perpendicular to this symmetry axis. So some things to be observed from deformation is that before deformation, a straight beam marked with horizontal and vertical grid lines. After deformation, the horizontal lines curve, the vertical lines remain straight but rotate. Compression in the top portion and tension in the bottom portion, and the neutral surface remains unchanged in length. So deformation is not constant over the entire cross-section. By considering an element of length change in x, it is possible to define the strain at a specific section on the cross-section. So change in s is equal to the length of segment at height y from neutral axis, which is equal to the change in x before bending. And the change in s prime is equal to the length of segment at height after deformation. So normal strain due to bending is equal to epsilon is equal to the deformation divided by length, which is equal to the change in s prime minus the change in s divided by the change in s. The above notation can be represented in terms of both the location y and the radius of curvature rho of the longitudinal element. So before deformation, the change in s is equal to the change in x, and after deformation, the change in x is equal to rho times the change in x. So strain distribution is strain is equal to the limit of the change in theta as it approaches 0. Rho minus y times the change in theta minus rho times the change in theta divided by rho times the change in theta, which is equal to y divided by rho, which is equal to negative y. So the diagram shows the usage of Hooke's law. Stress is proportional to strain, which varies linearly with distance y from the neutral axis. Following the equation, stress is equal to negative y divided by c times stress max, where c is the maximum distance from the neutral axis. The diagram illustrates how normal strain and stress distribute linearly across a beam under bending. The neutral axis experiences zero strain, while the top fibers undergo compression and the bottom fibers experience tension. Using Hooke's law, stress is shown to follow the same linear pattern as strain, with maximum values at the top and bottom of the beam. So in summary, we found that bending causes both compression and tension in a beam. The neutral axis remains unchanged in length. Strain varies linearly across the cross-section, and stress distribution follows Hooke's law.